started. So welcome to this time's Cape Advanced Technology Lecture. And today we're very delighted to have Professor Cheng-Wei Qiu from the National University of Singapore to give a talk. Professor Qiu was appointed the Dean's Chair Professor twice between 2017 and 2020, and then 2020 to 2023 in the College of Design and Engineering in the US. He's a fellow of Optical, SPIE, and the Electromagnetics Academy in the US. He's well known for his research in structured light and physics. He has published over 460 peer-reviewed journal papers. He was a recipient of the SUMMA Graduate Fellowship in Advanced Electromagnetics in 2005, and the IEEE's Graduate Research Awards, etc., etc. It's too long to read all of them. So I cut it short. And then he was highly cited researchers in 2019, 20, 21, 22 by the Web of Science. As an overseas partner, he has been awarded the China Top 10 Optical Breaking Through for 4 times, and he has been serving in the associate editor for various journals, such as Jose B, Photonics X, and the Photonics Research. And then he's also editor-in-chief for eLight, is a new journal for the fast publication. He also serves in the editorial advisory board for Laser and the Photonics Review, Advanced Optical Materials, and the ACS Photonics. The title of his talk is Low Dimensional and Waals Meta-photonics. Professor Qiu.
Well, I would like to thank Professor Qiu for hosting my talk. And today I'm very happy to to deliver this talk in this building. And this building is well known for the low dimensional material, or AKA, in particular, graphene, of course, beyond. So my name is Cheng-Wei Qiu, or in Chinese, it's Qiu Cheng-Wei. So I just put my characters to show my ethnic origin. So I'm working in EC department in US. And I think just now, Professor Qiu asked me where does this tree comes from? This tree comes from nowhere. I just put it here, but I think you notice there's a black icon there, right? So I think I want to make a metaphor that if I assume this tree stands for the growth or the development of the graphene research or low dimensional research, it is so well grown that it is a nice field to work on, but on the other side, you have big shadow. How you gonna benchmark yourself or market yourself? So probably, if you work with the professors in Cambridge, probably it's like a double-sided sword. Good, but your expectation is also more challenging. So how to solve this kind of dilemma? I think maybe, as my title suggests, you should put something different together. So I put photonics to blindly marry low-dimensional materials or van der Waals materials. So yeah, that's how I put it. If you cannot step out the shadow, you put another one shadow times shadow, negative times negative, possibly negative. All right. Well, just a short introduction of where we are. It's here, below Malaysia, and it's how our faculty looks like. Okay, so now it goes to the part of my talk. So usually, of course, now COVID has been gone, most likely. So in the past, we usually were asked 3 questions. Now it's like a philosophical question set. What is it? Where was it from? And where will it go? So for meta-photonics or meta-surfaces, I think it comes from metamaterials. I think you have been hearing about this kind of too many times, so I will skip it, right? anyway, I would say that it is nothing different from more or less, I mean, share a lot of things from with phase antenna array, because if you can control amplitude and phase of each antennas, you can do whatever you want in terms of beam shaping. All right. Of course, when everything goes to a planarized surface, then it incorporates different kind of things like diffractive optics, interface science, and nanofabrications. So this is one quote by Pauly, but I think if we're dealing with metasurface, we're dealing with a big devil, meta devil. Okay, so of course, now we are more interested in knowing where this field could go. All right. Of course, I mean, this is quite my biased view. In this, in my review, we basically split into 4 directions to go. I mean, my personal views. Of course, I mean, just 4 examples. One is biomedical metasurfaces. Let's say if you can combine the metasurface with endoscope, for example, to turn the lousy, cheap endoscope to be a better one. And of course, quantum metasurfaces is something that is very ongoing. And the third direction is computational, what we call information metasurfaces, where usually it deals with microwave, right? And I think I'm more focusing on this part, the hybridization with 2D materials. To start with, I would quote this one as a very good example, right? So I think Professor Qiu must be very aware of all these kind of developments from the very traditional diffractive optics and nano optics, now metasurfaces, so on and so forth. But it all boils down to one key question: why we have to do metasurfaces, especially the optical metasurface, or the called meta lens. So compared to this kind of pattern, which shows you how you should design your lens set, mobile, also called the end product. So you can see the profile is actually changing, all right? And if you look at the true picture of how a lens set was made, it's actually quite sparky. And then people come in to say that, okay, now we can use metasurfaces to change the game, or at least to improve the performance in terms of the bulkiness or in terms of a chromatic aberration. So there are 2 very nice examples, and they all develop this kind of broadband achromatic metalens in the visible frequency. Nevertheless, I think all the demonstration is still within like 100 micrometer, maybe millimeter scale. So it is still quite challenging if you wish to push it bigger, and particularly mass production ready. It is still far from that. So first of all, if you want to make it bigger, there's one issue involved. For example, if let's say if we want to develop like a millimeter scale, even millimeter scale, not wafer size, millimeter scale meta lens. Now, if you want to say that I want to use one meta lens to override, let's say this kind of 13 or 14 diffractive optics element, yes, you can do it. But trust me, the design would be extremely difficult, all right? You can design it in theory, but you can never make it in experiment. So instead of using one to replace the whole set, our idea is leaving the traditional setup still there, but replacing only the most challenging part using our metasurface. So in this case, we would say it's not a zero-sum game, right? You should cooperate. So this way, we leave, for example, with using one as a demonstration. So of course, this lens will induce a lot of aberrations. But we use one surface, which can be made by lithography, for example, to balance it off. So that all the wavelengths in your white light, for example, passing through the center all the way to the edge will arrive at the same position, as well as the shape is kept. And the time it arrives is the same. So that you can check all the with and without this kind of meta character. The aberration is definitely shown in the case without. Right? So this is typically, we call it a kind of like a cooperation. So for example, if we use this kind of DES patent, which incorporates, if I remember correctly, 14 components, but there's only one component which takes more than 70% of the whole expense. I think if you check it, I think they have this product on their catalog, selling around $5,000. But I think 70% of the whole cost is from one single lens that needs to be polished carefully. So if I just keep the rest, but just using Metasurface to replace that particular component, yes, you do it. I mean, even though you still need to, pay a lot for the nanofabrication, but it must be much cheaper than what DES can tell you, right? But overall, the whole setup will maintain the performance in a very decent way, so that if you consider the RMS wavefront error, you can see that if I incorporate our system design, we have this kind of blue curve, so it is actually broadband. And if I can incorporate a third order dispersion, so-called GDD is second order. If I can incorporate third order dispersion, it's even wider in terms of bandwidth, in which I can guarantee in the aberration correction. Compared to the TOLAB and other Edmond devices, you can clearly see the difference. So our Metasurface can be maintaining the focal point quite precisely in a wide band, while the rest fluctuates. This is just a preset, okay, to show you that if you marry one to the other guy, if you marry them properly, it ends up with a happy marriage. Not always happen, but it stands a chance. I want to propose a so-called synthetic interface optics. In certain sense, I'm just talking about plus, minus, minus, sometimes multiplications. Okay, in a simpler form. So the way I start from this kind of research is actually inspired by this kind of work in the 5 or 6 years ago. So they use, let's say, HBN as kind of material to fabricate a meta lens. In that kind of work, of course, they use HBN because of the high index. So in certain sense, it's similar to using silicon to do it, because silicon can offer a high index as well. And they pattern it in a pillar array or make it like a finite zone plate structure. And they all focus alike. That's it. But it's not really, how to say, exciting, because you just change the material to another material. So we want to challenge ourselves by asking one final question. How thin that material, kind of van der Waals materials could be. So if you consider the thickness, all right, 245 nanometer thick. Now, if you consider the index, you can simply calculate the relative wavelength in the material. So actually, it is still wavelength thick, not very thin. All right. So the question is, can we develop one meta lens using monolayer TMDCs, transition dielectric metal modulator conductors? So the question is, if I really use one monolayer, let's say in this case WSE2 flake, how we can do it so that the light can be focused? So if you really think about this question, I think the answer is no. Because it's too thin. It's only like 7 angstrom thick. When the light passes through, no matter what, you don't have enough optical path to interact with this kind of monolayer. So indeed, we're just using the EBL to pattern a zone plate-like structures, meaning this empty slots here. Indeed, nothing happens. So before we give up, then the student just try the phaeton second laser to write the same pattern, and suddenly it appears focally. So we are quite amazed that now we actually develop a monolayer lens, but it violates the physics. all right? It violates physics. So what happens, which induces this kind of focusing? Then we find that actually the reason is if you use phantom sight laser to write this kind of slots, in the areas like this, it's not empty. It has particles aggregated. And this kind of aggregation is made of WO2 and tungsten oxide. And this kind of all small nanoparticles aggregate to each other. So that when the light passing through, you have a lot of multiple reflections based on the interface. So effectively speaking, the optical path length is virtually enlarged. So they can accumulate enough phase. So this is kind of nanoparticles aggregation was caused by the high power laser, which will make the Se atom out, while in the same process, the oxygen comes in to recombine with tungsten atoms. So in this case, we didn't violate any physics law because you have these kind of particles, okay? And then once we try to do the subtraction in terms of thickness, we want to do some addition. In a certain sense that if I really combine this kind of geometrical phase metasurface with low dimensional materials, what different things we can achieve, or at least something that cannot be achieved by the either party. So I usually take this hamburger metaphor. For example, if I consider one cheeseburger to be TMDC, the other cheeseburger as metasurface, when you combine these two together, if I give you a double cheeseburger or Big Mac, that's not exciting, right? For the two meatloaf together. So now it's in linear regime, it's not really exciting, but in a non-linear regime, it's different. So the reason why I propose this one is if I just look back to the hollow eye, for example, the spatial light modulator, usually the pitch size of this kind of pitch, pixel pitch is 36 micrometer. And if you really buy a very top end spatial light modulator now, it's still like 4 to 5 microns, if I remember correctly. Which means now if you have a flake of a high quality TMDC monolayer, it's around 10 micron or 20 micron, maximally speaking. It means that within this kind of flake, you can only have a few pixels covered. And it's really hard to, create a certain phase change, enough phase change or amplitude change, right? Because the size is too limited. However, this is solved if you combine it with Metasurface, because Metasurface, each pixel is only 600 nanometer. So out of 10 micron or 20 micron, you can squeeze enough number of such meta atoms. So this is exactly the example we propose. So we use this kind of geometrical metasurface and then put another monolayer on top. In this case, we use WS2, but you use WSE2, I mean, whatever, so many options to do. The principle is similar. So when the light coming through, this metasurface, this is a hole. So in here, the light matter interaction is very useful to interact with the monolayer, right? Second, this hole, the geometrical phase induced by the rotation angle of the holes. So actually it imparts a certain geometrical phase to this area above this metasurface. So the monolayer now will experience enlarged intensity as well as a certain initial phase with a certain pixel size of 600 nanometers, 600 nanometers, 600 nanometers. So it forms a kind of like a beamforming in a nonlinear process. So you can clearly see that if I send in the RCP spin up at omega after passing through the hybrid, and it goes back to spin up, but it contains a 4 theta geometrical phase. Theta is a rotation angle here. Because the geometric phase will convert to spin down with a 2 theta, and then this monolayer will absorb 2 spin down photons, convert to 1 spin up photons. And then 2 theta times 2 is 4 theta. So in this case, you can see that we can split out the RCP photons and LCP photons at in a far field directly. This cannot be achieved by either party. So this kind of marriage is so-called good marriage. you gain something that is synergetic. So after this kind of addition, you see what we can do with cascade. Cascade means more layers. Of course, I mean, this also boils down to one key question in the nonlinearity of 2D materials. The reason why we use 2D materials usually comes from the big Chi2, for example, of this kind of monolayer. However, the big Chi2 monolayer is only too thin. So it's something like, yeah, it's good, but it's not that good. You cannot use it. And what is worse is, okay, if we consider TMDC monolayer, let's say WSC2. So one layer, good Chi2, and you say, okay, I use 2 layers. Then there's no SHG due to symmetry. So 3 layers comes again, 4 layers gone. So it cannot be cascade. It cannot be, scaled up. So you have to think about how we can solve this question. It's very hard. Now we find that there's one material candidate that can solve this kind of a challenge in a very simple way by itself. So we call it, this is actually a material called NbO2, this kind of crystal. This crystal is so-called the weak interlayer coupling materials. So its Chi2 is pretty strong. I mean, almost comparable to the Chi2 of TMDC monolayer. And on the other hand, if you consider 1 layer, 2 layers, 3 layers, the Chi2 is maintained. It doesn't change almost against the thickness. So it's like in the middle. I mean, in the middle of TMDC and lithium niobate. Okay. So if you consider the bulk crystal and the monolayer, you can see the band gap is literally the same. So it means that you can cascade more layers of such materials. And if we consider layer number, for example, it's indeed showing that it doesn't change too much. It almost keeps the energy level the same throughout different layers, while the rest kind of typical materials in 2D material community, it's very changing in this few layers case. Okay. So we utilize these kind of things to develop so-called the thinnest SPDC quantum light source. We use 46 nanometer to do it because the G2 here can be measured in a quite decent way. While if you want to use lithium niobate, I think you should use a bulk material, and if 2D materials, you cannot get it, right? So it stands a very unique position in this kind of 2D so-called van der Waals material photonics. And after we developed this, we accidentally find that this material is a very good candidate for polarization optics. So if I compare the birefringence of NbOCl2 with rutile calcite lithium niobate in this kind of wavelengths, it's pretty good. Right? Not like fantastically good, but comparable. And especially in the UV, actually is almost 99.6% measured. So in this case, we find that this material itself has a very huge in-plane optical anisotropy, which can be used as kind of like a polarizer. So we find that, okay, if we consider in-plane anisotropy, you can always find a lot of papers talking about 2D materials, which has in-plane, which has huge birefringence or anisotropy. But most of them is actually, how to say, this case, your optical axis is perpendicular to the interface. So it means that the in-plane is isotropic. So assuming that you have like 10 nanometer thick flake, how are you going to use this as a polarization component? You have to align your laser within this kind of 10 nanometer thickness to shine through. I mean, this is really challenging, right? But in our case, it's all in plane. So when we fabricate or synthesize this kind of material, like a flake, then the light pass through, it will rotate. Okay, so this is very efficient. So this kind of so-called cascadable van der Waals materials is actually quite useful in terms of nonlinear optics as well as correlation optics. So the third part that I'm going to marry, the third pair that I'm going to marry is metasurface with certain semi-metal. In particular, I use graphene. Right? So of course, I mean, if I just try to generalize a little bit, semiconductors, semi-metals has its own uniqueness, especially like unlimited bandwidth, zero band gap. Of course, I mean, it has certain problem of low photo detection efficiency and weak light-matter interaction. But these two guys, these two can be easily solved externally, right? Internally, I mean, it's really hard to solve, but you can introduce external parties to solve this one if you cannot settle the problem from inside. So the point, the solution is we put this kind of man-made structures with graphene. Okay. I mean, nowadays people are trying to make fun of, but this is always happening, right? Something in the research, people say, what's the point of doing that? And then some interesting paper comes out, and you know, especially in the electrocatalytic effect, you put whatever into it, it gets better. But I think if I want to use graphene to do a so-called vectorial photo detection, it's different, because if you don't consider this kind of structure, you can consider graphene alone. No, you can't do it. So you have to rely on external parties to solve actions. So I would say that now, this part, you can design whatever you want based on the need. Right? So it is actually a playground of geometry. You can test it. I mean, everyone has its own design, and as long as it works, I mean, it may end up with a decent work. And at the same time, you can pattern the graphene plus your meta atom, your meta surface. You can curve it. So later I will introduce why I have to introduce these kind of three pictures. But I think first of all, say that I want to make my talk more, general. I'll say that why I have to do that. So first thing first is I want to create something out of nothing. So if I want to say my end application is photodetector. So usually we rely on the bulk photovoltaic effect, or in short, BPV effect. And if the material has this kind of BPV effect, it is a very good candidate for photo detection, because this kind of material will have polarization dependent responses, especially at a zero external bias. However, it has a price. The material must have this kind of broken emerging symmetry. So ferroelectric material is one good material to do that. Or if you use 2D materials or low dimensional materials, frankly speaking, you have to make certain string to it. But this kind of string thing is really hard to scale it up. Accidentally, it can make a hump, you transfer the monolayer on top. Yes, you can introduce a string, that's it. But it cannot scale up. So if I consider graphene, it is definitely not BPV material. Okay. But we can actually introduce this so-called extrinsic BPV, following the same terminology of chirality. So we have intrinsic chirality and extrinsic chirality, right? So extrinsic means it is from outside. So you can clearly see that now if I deposit certain, let's say, gold antenna, nano antennas on top of graphene, and then if the polarization changes, the input polarization changes, the photocurrent direction changes. So it actually maps the polarization to be detected and the current you measure. So you create a certain kind of mapping. So the next step is to make it rigid. So now we just making just a line, and gradually we increase this kind of horizontal bar to break the symmetry a little bit from 0 to 300 and 600 nanometers. You can clearly see that the photo voltage starting from nothing to and a strong extent. So it means that now you can detect these kind of things. So you can correlate your photo voltage with the polarization. And you can clearly see that now you can rotate your polarizations, and then the electrical readout will change as well. So you can detect in this sense. And we also want to highlight that this way is actually very cascadable, I would say. For example, if I only have, if I consider, so it is basically the gray dots. It has a little bit fluctuation, that's a reference error. And now I have 2 columns, 4 columns, 6 columns. You can clearly see that the photo voltage response is getting bigger and bigger. If you put more columns, you get stronger signals for the readout. And then if you rotate the bars, the other side, all the response is flipping sign. Okay, so it is so-called directional. So the currents can be, the electrical currents will also be flipping the sign. So you can consider it is very sensitive to the incident polarization now. For electrical engineering, I think the Kirchhoff law is KCL and Kirchhoff law has 2 kinds, right? Voltage and currents. So if I also define a certain 3-port stuff, and nowadays I can basically consider I sending a certain portion, let's say normal, and the linear portion is like along a certain angle, and you can basically read based on the reading of the 3 ports, and you can directly decide angle without bothering about the intensity of the light. Okay, so this version is actually quite robust in terms of linear polarization detection in the middle IR at a room temperature. Now, once we develop this one, we want to push it to the end to be very strong in terms of polarization detection. In this sense, we call it PR, polarization ratio. So we make a survey that different kind of materials. So they basically have different kind of reliance in terms of the polarization ratio that it can be achieved. So you can clearly see that the usual way, usual range is PR. The PR range is around 8 or 10. That's it from experimental point of view. And usually the polarization ratio will not flip in the sign, except for a particular ferroelectric materials, as I mentioned before. So what we want to do here is, can we, go into this end? Really speaking, infinity in terms of PR ratio. And the second aim that we want to achieve is, can we, sort of stay in here, positive PR as well as negative PR. But in both ways, we need it to be huge in absolute numbers. So we find that it's doable. Now, of course, your external particle, external metasurface needs to be tuned a little bit. The T-shape doesn't work this time. So you need to have 2 leaf size antennas. So now you have theta 1 and theta 2 to control. And of course, a PR is a so-called maximum current versus minimum current. Okay, speaking of that, I think if you want to have your PR sign flip, so it means that maximum J divided by minimum J, there's a ratio, right? So you have to make sure that one guy flips a sign if you rotate your polarization angles. Second, if you want to make this guy, the ratio huge, it's very difficult to make the numerator big enough, but it's very easy to make the denominator to be close to 0. Then you get infinity values. So you can clearly see that now, if I theta 2 equals 0, meaning theta 2 horizontal, and theta 1 I sweep 45 degrees all the way to 135 degrees. You can clearly see that the J max is positive, but J min, it goes through 0. So if you consider ratio, you clearly get this one, it blows up. You get infinity here, positive infinity, negative infinity. Of course, when you fabricate it using electrical EBL, I will never get this kind of probability values. So somewhere we are here. And now you can consider given these kind of structures, if you are sending polarizations and rotate your polarization angles from 0 degrees to 180 degrees, one round, enough, there's linear polarization only. So this best curve is the blue curve. You can clearly see that the photo response flipping the sign, meaning now you get positive readout to 0, then to negative readout. Okay. So the PI is going to be huge. And the best case scenario here is within this area, this gradient is around 10.4 microvolt per degree change. Meaning, now if you're sending a linear polarization to our photodetector, you change 1 degree, the readout changes 10.4 microvolt, which is, comparable to a micropolarizer filtered silicon detectors in the visible range. Now, that is in the visible, but ours is in the mid infrared. If you compare to, let's say, a lot of commercialized product for the mid IR detectors, you need to use a cooling device. But this is definitely not needed in our cases. So the third part in this drive that we want to see whether we can do something unique. So from linear polarization in mid-IR detection, now we want to do the on-chip circular polarization detectors in the mid-IR. So this is just giving you a sense of, how you're going to detect this kind of circular polarizations. So you need to have an optical table, and you have a lot of cameras, and in addition, you have another camera here to detect. So you cannot carry them over, right? But if we can follow what we have done for linear polarizations before, it's just giving you a chip. You can simply carry it away. So that's our final aim. And now it goes to the curved structure. So we consider if we can curve the graphene sheet, which is very easy. You get a whole sheet of graphene and etch it, just leaving a trajectory of a circular shape. And then you deposit the T shape along this kind of rounded shape. And that's how it looks like. And now we use this kind of structure to detect circular polarized light. And we find that in terms of this kind of 4 Stokes parameter, R0 has no response, so it is good. So for R1 and R2, the currents in each block, it depends on this fashion, which is following sine 2 theta. And for the R2, it's following more or less like minus cosine 2 theta. So it reminds me that if I put 2 electrodes here, it's sort of like here, then if I detect it, the response, it's literally speaking equal to the integration of the whole thing. So I think it's going to be quite straightforward, right? Integration sine 2 theta d theta 0 is going to a 1 full circle, 0 to 2 pi. Similarly for that. So you will find that now R0 is 0, R1 is 0. So the whole chip only responds to R3, the S3 parameters, so which is good. Now you don't have to do any post-processing. Once the chip, this kind of on-chip photodetector receives something, it only responds to the F3 parameter without bothering the rest of the Stokes parameter. So basically, how the structure looks like. So the integration, of course, you have to leave certain space here. So it is it's literally 340 degrees. And there's no, you don't have to do any filtering. So in usual way, it's like we want to detect a Stokes parameter. You have to, in terms of mathematics, you have to write 4 equations, and then you decide this kind of S0, S1, S2, S3, right? You have to do some math, but in our case, you don't have to. So once we finish this one, we find that when I look at this kind of integration, I find that sine 2 theta, cosine 2 theta, actually we don't need to integrate the full 360 degrees. It's 2 theta. So that's why we try 180 degrees. Because 180 degrees, sine 2 theta is also zero, which is good. You do less, you gain more, right? And exact control 180 degrees. No sacrifice, no approximation. So again, it shows like it only responds to S3. And once we finish the integration, we find that maybe discretized summation will work the same. So if I consider one patch here, so literally it's like a sine 2 theta addition. When theta equals 0, theta equals 90 degrees. You can get 0 as well. And that's not the end. We still want to use our philosophy of doing less, gain more. That's typical human nature, right? So what less we can do and what more we can achieve out of here. We find that if I can use less graphene, can we do more? So now instead of using a one sheet, I use graphene ribbons. On each ribbon, I deposit gold. So the zooming picture shows like this. Why this is good? We find that actually comparing to this one to this, you can see that it increased 5 times in terms of photo response. This is pretty good deal, right? You use less, you get 5 times better. But what's the reason behind it? If you consider you have the nanostructures and the graphene below, if you send a laser light to it, the hot electrons, after diffused into the graphene sheet, actually, if it is a whole sheet, it diffuses everywhere. So those kind of diffusion, horizontal diffusions, is actually wasted because your electrodes can only detect or only collect on this direction alone, right? So by doing this kind of graphene ribbon, now if you excite certain diffusion here, there's no way to escape. So all the electrons must be collected or tunneled along the directions where you can collect everything out of the electrodes. So in this case, less is more. And of course, dealing with this kind of circular polarization light detection. We also developed this kind of so-called, I wouldn't call it circulator, but it's very similar to circulator thing. So we have a WS2, then we have a titanium dioxide waveguide on top, and then you're sending different spins of lasers to it. And you'll find that one spin is going to one arm, the other spin going to the other arm. So if you consider this kind of experiment, you can clearly see that now. If you consider spin up, then it goes to this end. Then if you consider spin down, incidence goes to the other. So you can cascade it. So if you send a spin up here, it goes to 3. If you send it here, it goes to 1. Otherwise, if you use a different spin. Of course, the only difference you have to match with the values of the WS2 with some optimized geometry of the waveguide mode. I hope that we make stone gold. The last thing that I want to achieve is I want to get something unparalleled. Okay, and that's the way we develop. So it is still like we are dealing with a circular polarized light, but now this case we consider emission or lasing instead of detection. So basically we consider a certain slant perturbation metasurface, which means now the hole is slanted. It's not vertical. Okay. Later on, I will introduce why we have to make it slanted. Of course, the whole thing, the theory is actually not that difficult. The difficult part is how to make slanted nano holes in a very precise way. So we think about a lot of ways, and we consider this kind of so-called slanted RIE system that you put a wedge that you can purchase from the offshore. We actually purchase from Taobao. It's very popular in in research now. You can buy almost a lot of consumable things. And then we put a sample on top, then using the traditional RE. So once it's fabricated, then you put this sample back, then all the holes is slanted. Very, you can, the slanted angle actually was determined by the wedge, how precise the wedge you can purchase. So the theory here is now we have holes. So given a hole, you have two kinds of symmetry. One is in-plane symmetry, whether it's a rectangle, it's a square hole. The other one is outer plane symmetry, whether it's vertical or tilted. So I use alpha and phi here. Let me go back here. The alpha is to show the in-plane symmetry. The phi angle is the vertical symmetry. If both of them are zero, so if you consider the momentum space, kx, ky plot, we call it a V point. Now, if I break the in-plane symmetry a little bit, but still vertical holes, so the V point was split into two circular points, so a C point. Now you shift the hole tilted. You can shift these two C points. So one C point will go into the center again in the momentum space. And that makes our device only selectively can work or operate on one particular CP light. So that is actually typically important when we can develop this kind of chiral laser or chiral emission. So what we do is we put certain dye into the hole, okay? Or you can put perovskite into it or quantum dots inside it, whatever. And then if you pump it, you will find that you can get a very huge high Q emission here. So the Q that we measured is above 2,600. And the CD, circular dichroism, is reaching 0.93. And this is probably the best record that we can observe for the chiral laser now, chiral emission now, okay? And the PR intensity, you can see that it's purely RCP alone. There's no LCP because the structure itself prohibited. And that's why I will always use this figure to showcase the significance, because if we just consider high quality factor or CD, you have different ways to approach it. One is like oblique incidence, like Nikolai Zoludov's method. So they tilted the incidence. You can also get the chiral response. The other one is doing the anisotropy by absorbing. You can also do the circular dichroism approach to one. But in our case, we use a vertical and we want to have high Q and high CD and one spin only emission. And that's the first thing, first recipe to approach so-called intrinsic chiral BIC, bounded states in the continuum. We find that that is good for PL, but not exactly lasing. So we develop another perovskite stuff, and we call it chiral lasing now. Okay, you can click. I will not go through the details due to the time limitation, but I strongly recommend you to read this paper. And it was handled by you, right? Yes. Yeah, so really like this work because at first glance, it's like a marriage between PB phase and BIC, right? The bounded state in. But if you really look at the physics, I think if you just go along this way, you will never get it because the devil is in the details. The detail is in the supplementary materials where we introduce a typical mode. I still remember it's TM2 mode. Only this mode will get this one. You choose any other mode which gives you high quality factor, you don't work it. The reason you can read aside on. But overall effect is like if you pump it, all right, the perovskite will emit. But this kind of so-called photonic value, due to the structure, will lock up a certain spin to a certain diffraction channel. So you have different kind of chiral laser now. Okay, and perovskite itself is a good lasing material. So it's not a simple combination. Okay, it's a sophisticated combination. And I think lastly, I would just quickly go through the recent, some of my recent works on the van der Waals Meta-surfaces. And if you are interested, you can refer to these two review work. But of course, I mean, here we are talking about this kind of photon and electron hybridized, so-called quadrupole particles. So I'm still doing this kind of 1+1 thing. All I want to do is 1+1. First of all, not equal to, much bigger than 2. Or if I can get 1 to achieve 2, something like this. All right. Because I think the details sometimes are not appealing to the general audience, but the philosophy is universal. So the tristonics, this kind of magic angle physics, is already discovered by Cao Yuan in MIT, but it's for electrons. So we want to push it to the photon. At least we are working on the photodetector. So photo part, not yet before our work. So this is the first proposal that we came up. My student actually now makes this kind of graphene ribbon, and then you have 2 such ribbons stacked to each other. It's a ribbon, and you will find that if it's just 1 layer, this is dispersion. How dispersion looks like. 2 layers, you have because you have coupling, it becomes kind of like a circular shape. And if you operate at different frequency, dispersion changes for the phonon polaritons. Okay, so that gives us certain sense that we can tailor the dispersion of this kind of photonic, magic angle photonics. However, I mean, even though we publish in a very ACS type journal, but we don't have experiment because it's really hard. Graphene array, 2, really complicated. And then it drives us to reach a simpler version of experimental. So the key point is we try to get this kind of hyperbolic dispersion of 1 surface. So we find that some natural materials, MO3, is bound to be behaving like this. Now we just need to have 2 MO3 stack each other just a little bit. That's essentially equal to the previous example. That is very difficult to achieve. So we find that if I stack in a proper way of achieving this delta theta angle, especially let's say 70 degrees, you can consider dispersion. It's different. You experience certain transition angle here. And compared to the electron version, it's not that sensitive. Because if you go back to the magic angle, let's say bilayer graphene, for example, people usually tells you, oh, you have to use tips to nudge it so that it may be 1.1 degree or 1.15 or 1.2 degrees, totally relying on the operator's experience. But in here, optics, I mean, 70, 71, 72, more or less the same. So it's very robust. And of course, I mean, this kind of photon polaritons now enter a stage where you should care about how you can control the wavefront on chip once the polariton was excited. I will skip this kind of things because it doesn't follow our the main thing. The main thing here is I want to achieve 1 to 2. So still, you have to arrive at this kind of photon, magic photon, photonic magic angle using 2 MO3. Can we use 1 material to do that? Because 2 layers, you can control the twist angle. How about 1? Looks like you have 1 missing degree freedom, but you definitely need to have 2 degree freedom to play with. So we find that actually, interesting speaking, we read a paper in PRB, published in 1970s, I think, and they actually tell us that the calcite has kind of like a hyperbolic infrared photon polariton response, meaning in this range, in the infrared, calcite exhibits, let's say, hyperbolic dispersion, meaning if you consider the tensor of epsilon, so you have 1 positive epsilon and 1 negative epsilon by its nature. You don't have to bother with that or fabrication or engineering. You buy a calcite, that's it. But usually we only care about the optical regime performance for calcite because it's very good birefringent material. Right? the double refractions. No one really care about the infrared for that, and we care about this. It's especially because we, based on our past research interest, and we find that now you can use in one material, but now you need to care about how you play with 1 to 2 game. So let's say if you purchase other thing, let's say if you purchase such a bulk calcite crystal, okay, and if assuming because calcite is birefringent, so you have an optic axis. The optic axis is like this. This one definitely doesn't work because it's too rigid. Now, if you consider, you have to consider a polishing surface, tilted polishing surface. So once you polish the surface and the optic axis is not vertical, like this. So you're polishing this way and put on the top of the optic table. Then you see a surface like this, but the optic axis is tilted. And in this case, it's exactly what we have done here. And you will find that this is really amazing that now, once you're using a chip to launch the photopolariton wave, the K has real number and imaginary number simultaneously. So in the past, if the propagation wave K is real, if evanescent wave K is imaginary, now you have both. So that's a very interesting phenomenon. And we just do the experiment since we purchased a spec in the probe station. So that's why we call it ghost surface polarity. All right, then later on we just arrange some other crystals that is monoclinic, and asymmetric is even larger. All right, so I think I used up all my time, and I want to conclude in a very simple way. I think our limit has reached in terms of the span of attention. So what I'm trying to say here is, as an electrical engineer or optical engineer, it's really hard to invent brand new theory, but we can combine materials, resonances, symmetry, and structure together. And once you combine it, or you call it integrated, it's better to get something out of these kind of things, which cannot be achieved by individual elements. All right. So, but anyway, always people ask, let's say this kind of photopolariton, ghost polariton, metasurfaces. Usually the question will be followed, what's the point of doing that, or what application it can have? This is the excuse that I usually try to prevent you from asking particular questions. All right. I want to thank my funding agencies and the collaborators, and that's my final slide. I'm asked to promote this. Done that before, but as a chief editor-in-chief, I cannot say no to my boss. So anyway, you look at it, and just to show you a certain projection and impart certain hope in your mind. And of course, I mean, I never prevent you from submitting to make materials, for example, first, but they cannot digest all the good submissions. Welcome, right? And this is our data. All right, to give you a certain hope that we will not basically frustrate you, and we will do every kind of manner to help promote your work in all sorts of media, technically, scientifically, and socially. All right, and this is basically our team. Professor Da-Ping Chu is also one of our editorial board member. And that's all for my talk today. And thank you very much for your attention.
Thank you very much for sharing with us your exciting journey in exploring different areas of directions. So now the talk is open to questions.
Politically correct, I switch to this slide.
Yeah, perhaps I just have a question on the BIC system.
Yeah.
So essentially, actually, you're kind of exciting with the laser, like a monochromic laser, and you're observing this kind of circular polarization happening, right? Image. So is there any wavelength change according to your experiments, or?
The wavelength shift is quite small. It's only around 5 nanometer.
All right.
It's pretty stable because we choose a typical mode. That mode is very special because it's a circular mode as well. So this mode will be quite stable. If you choose another mode, for example, TM1, for example, instead of TM2, you will not get such a sharp resonance. The FWH, the full maximum will be quite broadened.
All right. Okay.
So the mode selection is very typical.
And also, you have this angle dependence of your like slanted structure.
Yeah.
So do you also observe like elliptical emission or a light or?
Yeah, you will.
Right.
Yeah, that's why we have to.
You have to tune, right?
Optimize the alpha and the phi
Okay.
to form a certain good relationship.
All right. Okay.
Yeah, then you fabricate it. That will give you perfect CP light emission.
Any other questions?
Professor Qiu, for your wonderful presentation. So my question is, the mass fabrication of dielectric Metasurface, particularly for like imaging optics, is like a common problem. Probably it's a bottleneck for Metasurface applications. So how do you envision this can be solved or addressed in the near future?
Yeah, that's particularly the question that I want to avoid. So first of all, you ask the wrong person because even though I'm working in electrical engineering, I'm still a more fundamental researcher. Second, I can give you hope anyway that visible frequency is really hard to manage, but you can move on to the infrared because wavelength is slightly longer, and then you can rely on certain optimization algorithm. For example, you can consider subwavelength features, right? But you can force in your design that 2 or 3 subwavelength features stick to each other, and then the element is actually non-subwavelength. Then you can use nanolithography or nano imprinting technology to do it for the infrared stuff. And one of my former PhD students, he has a company, Metalin X in Shenzhen. Actually, all his product is working on surveillance and the infrared imaging stuff. Actually, the business is running so well that it is soon to be IPO. And we particularly avoid the visible frequency. I leave this one to Nikon, Canon, others company, right? Yeah, so using another imprint, you can only just make a mask, a mask. Then you can do a lot of fabrications. Yeah, but it depends on how you optimize it.
Another question. Could you provide more detail how they fabricate Metasurface with imprint?
It's like because now your every element is above one wavelength. So if you consider infrared, it's like micrometers, right? So it means that all your features, you don't have to go with EBL. Then you just make one mask from Japan or from elsewhere, and just imprint it. So you can imprint multiple times. So that's actually one kind of way to approach mass production.
So their Metasurface itself is imprintable.
Yeah, it's nano imprint. Based on nano imprint, you can make it many times until the mask is broken.
We don't have front room. Let's look at the online. We have people try to ask questions online. Question. Thank you for the insightful talk. What are the prospects and feasibility of Metasurfaces for quantum technologies? And so additionally, which 2D materials are more favorable or easier surfaces for practical application? First one is about prospect and the feasibility of metasurfaces for quantum technology.
So there's certain easy way to go with. First of all, is like if you can design certain optoangular momentum metasurfaces, so you can easily achieve certain entanglement, quantum entanglement out of this kind of method. So this is one easy, feasible way to approach quantum technologies. But of course, quantum technologies are very broadly defined. So I'm only talking about from the optical and photon way. So the second one is which 2D
materials are more favorable or easier to integrate with metasurfaces for practical applications?
I would say none. Because it's like a, if you consider thin layers, but the efficiency is not good. If it's for bulk, you can use lithium niobate. So of course I want to promote my own stuff, and the OCL2 is in the middle. So I think that material is very interesting. So so I want to market myself.
So let's keep it as an open question, still to be investigated. That's probably we have the questions from the online. No further questions from here, and thanks the speaker again. Thank you very much. Now closed. Thank you very much for the attending.
Thank you.